what we are doing here is taking the Lewis structure and from the Lewis structure, we have an idea of how the atoms are arranged around, say, a central atom. And sometimes a chemical can have more than one central atom, but there's going to be a rule by which these atoms are going to arrange around a central atom. And that's based on the fact that these things want to avoid each other. But from that, we come to something called the valence shell electron pair repulsion theory. It's called VSEPR. So that will tell you about the molecular geometry. And the molecular geometry kind of tells you the shape of these things. And from that geometry, you can tell some properties of these chemicals. In fact, the properties of the chemical, the macroscopic properties of the chemicals are dependent on the molecular shape. Like, for instance, let's take a look at what we have right here. If you take a look at this carbon atom, you see that it's got 1, 2, 3 atoms that are stuck to it, but they're going to be arranged in such a way that they're as far apart as possible. So the geometry around this carbon is what we call trigonal planar. Okay, and there's going to be several geometries around these central atoms over here. And when you put it all together, it gives you the shape of a chemical. And that's what you see in this space filling model. So that's just a preview of what is in store in this particular discussion. For those of you who are going to go into medicine, or maybe you're going to go into pharmaceutical field, the shape of these chemicals are very important in terms of their therapeutic properties. So it tells you right here that shapes and sense of smell is critical. The way we smell fragrances or even odorous chemical is based on the shape of a chemical. What happens is in our nasal membranes, these chemicals that are airborne lock into these certain cells, and depending on the shape, it triggers a response that we either indicate as pleasant or offensive. So, video.
Specific airborne molecules, referred to as autogens, results in the sense of smell. As the autogen is inhaled, it moves through the nostril and into the nasal cavity. There it comes in contact with the olfactory epithelium. The olfactory bulb, which lies above the nasal cavity, receives sensory information from the olfactory epithelium. Within the upper nasal cavity, the autogens dissolve in the mucus lining, where they can interact with receptors on cells in a specialized region on the olfactory epithelium.
So you can see that, again, that our physiological response is dependent on chemicals. And the response that we have is dependent on the shape of these chemicals. So let's take a look at this, because this is pretty interesting. If you take a look at these chemicals, you'll see that it looks like there's only one type of chemical that you see here. But in reality, if we, let me just make sure everyone's quiet.
What's the yellow bar on the top?
Because mute all except me. As people come in, they forget that they're
what is it asking you to do?
Okay. So let me go ahead and continue here. What happens is that you might think that there's just one chemical in the bottom left, but in reality, if we take a look at this, you see that that right there is the molecular structure of codeine. That right there is the molecular structure of morphine. And that right there is the molecular structure of heroin. Now, I've got some experience with morphine because when I was in an accident when I was doing my postdoc at Columbia University in New York. What happened was I was in a restaurant, and this was late at night. I was just finishing some research that I needed to take care of for the next day. and my buddies and I, other postdocs, one was from Italy, another one is actually a professor at UCLA. We went to the pub to just kind of like wind down the day. But the next thing I knew, I was waking up in the hospital. I guess my radio bone was shattered, and I was just trying to get into the ER. What apparently happened was that a car came crashing through the restaurant, and I think someone described that there were bodies flying everywhere. So this happened at about 1 o'clock in the morning. Anyway, I'm recovering a few days later, and I'm in pain, and I'm asking the nurse. Well, the nurse asked me if there's anything that they can do to help me, and I said, "Yeah, is there anything you can do for the pain?" And he says, "Yeah, there's an IV flu bag here, and if you change this uh, device, you could actually give yourself some morphine." And so that's my experience with some morphine. It was like the best thing ever. It sort of took care of the pain that I was feeling, the discomfort. But you can see that morphine is very close to the structure of codeine and heroin. And in fact, these things can be very addicting. The other chemical that you see, and again, the chemical over here is actually um, amphetamine, and it all has this backbone that somehow fits in certain parts of our brain to give us a response. These two right here are oxycodone and hydrocodone. And so, again, molecular shapes are so critical in terms of their potency. In terms of how cocaine works, that's another chemical. Usually, the way our synapse works is that there's these chemicals that goes from one synapse to another, but codeines block these things, and so they make it unresponsive. So let's take a look at this video so that you can see what's going on.
Our brains are composed of networks of billions of tiny nerve cells. Signals race around these networks, crossing the gap between the nerve cells using chemical messengers. One network is dedicated to making us feel good when we do something that is essential to survival, such as eat, drink.
Cocaine blocks something called the dopamine transporter. And what that does is it mops up dopamine that sits in the space between two cells. And if that reuptake is blocked, what you get is an awful lot of dopamine floating around this space.
The flood of dopamine sends the feel-good network in the brain into overdrive, producing a sense of euphoria and self-assurance, making the user more animated and talkative.
So you can see that, again, how chemicals affect our brain chemistry. So it's important that you understand why the molecular shapes are important, and then we're going to take a look at how to determine the shapes of chemical. So in terms of the theory behind it, it's called the valence shell electron pair repulsion theory. Okay, and the idea here is that the valence electrons, which you guys know is the outermost electrons, are going to be responsible for the shape of the chemicals because they want to be as far apart as possible. So this is actually an extension of Lewis structure. You need the fundamentals of Lewis structure because if you don't have the Lewis structure of a chemical down, then you don't know how it's going to arrange themselves. And then the main premise of this particular theory is that valence electrons, the pair, because electrons are always in pairs, even though they're negatively charged, and so you think they'd repel each other, but because they have opposite spin, it sort of stabilizes it that way. That's why you can have two electrons in an orbital. But they want to, whenever you have one pair in close proximity to another pair, they're going to repel each other. And so they take on a geometry that places them as far apart as possible. The driving force is the Pauli exclusion principle that says no two electrons can occupy the same space if they have the same set of quantum numbers. Of course, when two electrons are in an orbital, then one is positive spin and the other is negative spin. So the electronic geometry is in such a way that they want to minimize electron repulsion, and then the way the atoms sort of fall out from that gives you something called the molecular geometry. In the electronic geometry system, we call it the AE system, where A is the central atom and E is the lone pair. When we go to the molecular geometry, we introduce B, which are the bonded atoms. So this is just a form, a notation to give us an idea of how to classify a central atom in a chemical. So what are the different types of geometry available? Well, when you have two lone pairs around a central atom, then that geometry is going to be linear, okay? So if you had a lone pair here, and that's a pair of electrons, that's a pair of electrons, then the natural geometry is placing these lone pairs as far apart as possible. When you have three lone pairs, then the geometry is a trigonoplanar, okay? Where the bond angle is going to be 120 degrees between atoms or between lone pairs. If you've got four lone pairs, and this would be satisfying the octet rule, then you would have a tetrahedral geometry in which the bond angle, you have to look at 3 dimensions now, are about 109.5. In chemistry 200, what happens is you have the valence shell expansion, and so the central atom is going to have more than 8 electrons, and so you get geometries like this, which is called a trigonal bipyramidal. And it's called a trigonal bipyramidal because in this axis, you have a trigonal geometry, but then you have something up and down. And so that's why it's called a trigonal bipyramidal, because there's a pyramid on top and a pyramid on the bottom. Then if we have 2, 4, 6, 8, 10 electrons, 12 electrons, I mean, then we have something called the octahedral geometry. The octahedral geometry. And the name octahedral comes from the fact that there are 8 faces in this particular geometry. 1, 2, 3, 4 on the top and 4 on the bottom. That's why it's called octahedral. Okay, so let's take a look at this real quick. And here they're showing you the VSEPR. I'll go ahead and talk about this theory. And when you have one lone pair, then of course you just have that type of situation. Then what could happen is that you could have a central atom that will have 2 lone pairs. And when you have 2 lone pairs, it looks like you have linear. And then when you have 3 lone pairs, you have trigonal. And when you have 4 lone pairs, we have tetrahedral. Okay, and that's the extent but by which you guys are going to be exposed to. But know that in chemistry 200, you do have more than 8 in the central atom, because now you can use the d orbitals, and so you can have these other geometries: trigonal, bipyramidal, and octahedral. Make sure I have my chat on, just in case there's questions. Okay. Yeah, water is going to be a very good chemical by which there's going to be, it's tetrahedral, and there's 4 lone pairs on the oxygen, and 2 of those lone pairs are actually going to be occupied by hydrogen to form the bond, and you'll see exactly how that works. So let's continue on with VSEPR. And the idea here again is to make sure you have a geometry that keeps these lone pairs as far apart as possible. So the first thing that you would need to do to do this VSEPR analysis is to determine the Lewis structure. And you'll see why shortly, why this is important. It'll help you determine the number of bonds in a chemical and then identify the central atom. And then once you finish the Lewis structure, you can come up with the electronic geometry. You need the electronic geometry before you can get to the molecular geometry. Okay, so the electronic geometry has to do with how many uh, electron domains are around the central atom. You could have a linear, a trigonal, or tetrahedral. Those are the only type of geometries that we can have based on electronic. And then from the electronic geometry, we have the molecular geometry. And the molecular geometry requires us to replace these valence electrons with atoms for certain chemicals and make them bonded atoms. Okay, so this is how we determine the molecular shape, the molecular geometry of a chemical. So before I go into the main theory, let me sort of explain to you what's going on. If you have a central atom, like here, that's a central atom. Okay, here that's a central atom. You can think of a central atom as the hub on a wheel. It's the centerpiece of a wheel. And so I'm just going to put an A right there to indicate that's where my central atom goes. It's in the center. And things come out of it like lone pairs and bonds. And so if you have a single bond, then this is what we call a single domain. This is one domain right here. Okay, because it's pointing in one direction. And we can think of it as a spoke on a wheel pointing to something that's connected. But if we have multiple atoms, but it's connected to if we have multiple bonds, but it's connected to one atom, like you see here, then that is considered one domain as well. Even though it consists of 3 bonds or 2 bonds, that's one domain. Okay. Again, a domain is a region of electron density that's pointing at a specific region, at a specific space. And then if we have a lone pair occupies its own domain, and that's what you see right here. Okay, so in this particular situation, what we have is 3 regions of electron density, or 3 domains. Electrons are considered its own domain. And so what we can say is that we have an AE3 system right here, because this is the first domain, second domain, third domain. So the electron pair, even though we have multiple bonds here, has to do with electron regions or domain. Some books like to call it electron region, some books like to call it domain. I'll use either one. Okay, and then what happens here is that 2 of these electron regions here, let me change my pen color, here and here are actually have atoms at the end. So this now becomes AB2E, where one of the electrons pair is still an electron pair. Okay, so again, let me try and remind you, this really simplifies things in terms of how you can determine what category you have. You need to look at the central atom as the center of a hub of a wheel, and then you have to look at how many spokes come out. If it's one atom, if it's one bond to a single atom, that's one domain, one region of electron density. If it's multiple bonds, but it's going to a single atom, then that's another domain, okay, or region of electron density. And then if it's a lone pair has its own domain. So that's very critical, because if you don't get that down, then you're not going to be able to classify what type of geometry you have. So let me move on and let me show you some examples. Here we have BH3. Boron is one of those chemicals that is an exception to the octet rule. It's only satisfied with 6. But if you look real closely, you can see that this is 1 domain, 2 domain, 3 domain. So this is an AE3, which is now an AB3 system. There's 3 domains around that particular chemical. Remember, you're always looking at the central atom, and you're looking at how many spokes come out. Let's take a look at that. That's methane. you guys already know that has 4 domains. 1, 2, 3, 4. Okay. If you take a look at this, let me clear oops. Let me clear my, you can see that this right here is formaldehyde. The central atom is that right there. And coming out of that carbon is 3 domains. 1, because that's, even though that's a double bond and there's 4 electrons here, it's pointing in one direction. So that's 1 domain, 2 domain, 3 domain. Do not confuse yourself with the electrons on that oxygen. That's not a central atom. So that doesn't count. You're only looking at the central atom right here, and you're looking at how many spokes are coming out of that central atom. Okay, so far so good? I hope so. Here, this is the central atom, and you can see there are 2 domains. Okay, here, again, this is the central atom, and there are 2 domains. Don't confuse yourself with the lone pair at the terminal atoms, because that's not going to dictate the geometry. It's always the central atom that dictates the geometry. Here, this is urea. There are actually multiple central atoms. The nitrogen is the central atom here, and the carbon, but we're paying attention to this carbon, and you can see that there are 3 domains around that carbon. It's really that easy in terms of counting domains or regions of electron density. This is ammonia. Let me clear my slate here. Okay, this is ammonia up here, and you can see that this lone pair counts as a domain. So there's 1, there's 2, there's 3, there's 4 domains around ammonia. That's why you need the Lewis structure, because if you don't have the Lewis structure, you don't know that that nitrogen has a lone pair on it. Okay, and the lone pair makes a big difference. This is ozone, this chemical right here. And if we count the number of domains, and hopefully you guys already are ahead of me, that's 1, that's 2, that's 3. That's 3 domains around that. This is the central atom around that oxygen. Okay, and then this is nitrogen dioxide. Again, you can see that there are 1, 2, 3 domains on that NO2 chemical. So it's easy as that, but the key to identifying how many domains is to know the Lewis structure, because if you don't have the Lewis structure, then you can't count domains around the central atom. This finally is water, okay? And water has 1, 2, 3, 4 domains, okay? So why are the domains so important? Because the domains tell you what category you have. And remember, only limited to 2, 3, or 4. Let me go back. This right here would be 2. This right here would be 3. This right here would be 4. Okay. In this course, we're only limited to 2, 3, or 4. In Chem 200, you will have 5 and 6, but don't worry about that for now. So whenever you have 2 domains around a central atom, its electronic geometry is automatically set for you. It's AE2. That's a linear geometry. Now, if these lone pairs actually have atoms at the end, so there are 2 bonded atoms, 0 lone pairs, then it now becomes an AB2 molecular geometry. And that chemical will always be linear. And let's go back. See how, let me clear this. Carbon dioxide is linear. You see how hydrogen cyanide is linear? Well, that's because it's only got 2 domains. Even though this looks linear, that has 3 domains. So that's not a linear chemical. What you will see is that because it has 3 domains, we're over here. Its electronic geometry is AE3. Its skeleton is trigonoplanar right here. Now, if all 3 atoms or all 3 domains are bonded atoms, then the molecule will be trigonal. So let's go back here and let's see where we have that. This is an example right here. This is 1, 2, 3. No lone pairs. They're all bonded atom. That chemical is trigonal. Let's look at this guy right here. That 1, 2, 3. The geometry around that carbon is trigonal. Here we have 1, 2, 3. The geometry around that carbon is trigonal. You see how easy that is if you know the domains? Well, what happens if you've got still an AE3 system, 3 regions of electron density, but only 2 of them have bonded atoms, and then you have 1 lone pair? Well, let's go back. This is an example right here. Let me clear my slate. This is an example right here. There are 3 domains, but one of them is a lone pair. This is another example. There are 3 domains. One of them is a lone pair. So what is the geometry around that? Let's go over here. We've got a system code AB2E. And because you can only see atoms when you're looking at molecular geometry, the structure is bent because its skeleton is trigonal. So these chemicals right here are actually bent chemicals because this lone pair on top pushes these atoms away. This nitrogen is going to be bent as well because this lone pair on top pushes these bonded electrons away. That's why it's called bent. And then we also have to say it's bent trigonal. Bent trigonal because there's also a bent structure in here, but that bent structure comes from a tetrahedral. This bent structure comes from a trigonal skeleton. So we have to distinguish one bent geometry from another bent geometry. So I hope you're hanging with me, okay? Usually, because you guys are taking things online, you guys will have access to this chart. You have access to this chart. But if you get to Chem 200, make sure you memorize this. And if you think about it logically, these geometries naturally fall out just based on the premise of the valence shell electron pair repulsion theory. That is, regions of electron density wants to stay as far apart as possible. So they take on a geometry that places these regions as far apart as possible in a geometric shape. Let's take a look at 4 regions of electron density. When we have 4 regions of electron density, and this is our example right here, this is our example right here, this is our example right here, 4 regions of electron density. What happens is that the basic skeleton is tetrahedral, but if you've got atoms at the end of each one, then the molecular geometry is AB4, and that's tetrahedral. Here, if you've got only 3 of those 4 regions with bonded atoms, then that's, sorry, I don't know why that zoomed out. Let me go back. Okay. Okay, here we go. My Zoom keeps messing me up. But again, going back to 4 regions of electron density, we have it right here. If all 4 are connected, then our molecular geometry is straight tetrahedral. If 3 of the 4 are bonded atoms and 1 is a lone pair, then we have a pyramidal. And if 2 of those regions of electron density are bonded atoms and 2 lone pair, then it's a bent tetrahedral. Okay, and that's what we see right here. This would be AB2E. That would be a bent tetrahedral. This would be an AB3E. That would be a pyramidal. and this is an AB4, and that would be straight tetrahedral. So it's that easy in terms of coming up with the molecular geometry, especially if you have this chart right here. If you have this chart, then you can just figure out how many domains, how many bonded atoms and lone pairs, and then you can come up with the molecular geometry. And with the molecular geometry, you also get shapes and bond angles. This is about 180 degrees. This is about 120 degrees. This right here is less than 120 degrees because these lone pairs right here push those bonded atoms away. This right here is 109.5. That's the bond angle in a tetrahedral geometry. This right here would be less than 109.5. And this right here is even much, much less than 109.5. So you come up with geometry just based on what type of atoms and what type of shape you have. So these are just examples, and I'm going to go through these real quickly. You can see that there are two domains around carbon dioxide. They have two bonded atoms at the end. Of course, the electronic geometry is AE2. The molecular geometry designation is AB2. And this is what it looks like. This is the space filling. Okay. These are examples right here. This right here tells you what atomic orbital, an S and a p orbital, is responsible for that shape. We will get into that later. In Chem 200, it's very important that you understand something called molecular orbital theory. There's a question here. What's the difference between a trigonal bend and a tetrahedral? It's angle, but also the skeleton. If you look at the skeleton here is based on a trigonal planar. The electron regions are separated by 120 degrees. Here, the skeleton, that is the framework, is tetrahedral, and the bond angle is about 109.5. So it looks the same because what you have is a central atom connected to two other atoms, but one has a skeleton that originates from a trigonal. So there's a lone pair here. Another is a skeleton that comes from a tetrahedral. Of course, when you look at molecular geometries, you don't see pairs of electrons. All you see are atoms. But the skeleton, the reason why it has that tighter angle here is because there are two lone pairs in the tetrahedral bend. Okay. So again, that is an AB2. This right here is an AE3. And again, you can see 3 regions of electron density. So if all 3 are bonded atoms, then the molecular geometry is trigonal. If only 2 of those 3 are bonded atom and you have a lone pair left over, then you have a bend. These are the bond angles. The atomic orbitals that make this up, okay, is 1 s orbital and 2 p orbitals, either a px and a py or py and a pz, but 2 of the p orbitals make up this type of molecular orbital, okay? That's why it's called an sp2. sp2 will always be a trigonal electronic geometry. And here are some examples, and here are some pretty pictures to illustrate what I mean. Let's take a look at the last category, the 4. So when we have 4 regions of electron density, then we definitely have a tetrahedral electronic geometry. And if 4 of those electronic regions are bonded atom, then the molecular geometry is also tetrahedral. And the way the atomic orbitals are arranged is 1s, and all 3 of the p orbitals are mixed to form that molecular orbital. And here are some examples of chemicals that have these. If we have 4 regions of electron density and only 3 bonded atoms and 1 lone pair, like in ammonia, you don't see the lone pair here, but they're there. Okay, that's why it causes that thing to take on a pyramid type shape, that chemical to have a pyramid type shape. So the molecular designation is AB2, AB3E. There are 4 regions of electron density. It's a pyramidal shape. Okay. If you've got 4 electron domains or 4 regions of electron density and 2 of them are bonded atoms, then what you have is the following. You have 1, 2, 3, 4. This thing looks bent, as you can see from this diagram, and that's because these pair of electron density that you don't see are causing those bonds between the hydrogen and oxygen to be as far apart from the lone pair. And to be as far apart from the lone pair, it has to take on a bent shape. But this would be designated as bent tetrahedral because, again, the framework by which this thing comes from is tetrahedral. It's got 4 electron domains. Okay, it's got 4 electron domains. So again, this is a summary of this table. This is a very handy table to determine molecular geometry. This is a summary of what we call hybridization. You guys will see a lot of this in Chem 200. The hybridization, hybrid is kind of like a mixing, okay? It's a mixing of certain things. When you mix an s and a p orbital, then you have this linear geometry. When you mix an s and 2p orbital, you have that trigonal geometry. These are all electronic geometries, by the way. And then depending on how many of those regions of electron density are replaced by bonded atom, then you get the geometric molecular geometry. Here, when you mix the s and 3p orbitals, you have an sp3 hybridization. In Chem 200, you guys are also going to be introduced to this, which makes it a little bit more complicated. These are chemicals that doesn't follow the octet rule, that takes on this geometry right here, okay? But that's for Chem 200 in terms of a lot deeper level. For you guys, you're just going to be introduced to the fundamentals here. And then as you become masterful of these fundamentals, we're going to hit you with these more complex geometry. So you can see that once we have an idea of the geometry of chemicals, then we can go to more complex chemicals and figure out what the geometry is around each central atom. This right here, I believe, is caffeine, and certainly my favorite drug of choice. I had much of it this morning. What you see here are many central atoms. This is more complex. This is a central atom. This is a central atom. This is a central atom. Thing about chemistry is that chemists are generally lazy. And so what we do is that we have all these shortcuts. And one of the shortcuts that we are notorious of is that if we have, let's say we have this chemical right here. This chemical is called ethane. That's the name of this chemical. Okay. This chemical is called ethane. And it's a very simple chemical. It's got 2 carbons and 6 hydrogens. But what we want to do is, you see how long it took me to draw this structure? I want a shorthand notation so that I don't have to keep drawing the hydrogen. So what I can do is I can just draw 2 lines. And the ends of this line represents a carbon. And because carbon always has 4 bonds, the hydrogens are implied. So let me kind of construct what I mean. If I have 2 lines and the end of these lines are carbon, then I can put a carbon there. And then I always know carbon has 4 bonds. So right now this carbon has 1. That means it needs 3 more. And those 3 are actually hydrogens. Okay? So this carbon also has one bond already shown. It needs 3 more to have 4 bonds, and those are going to have hydrogen. So you see how I took this simple structure and constructed that molecule? I can also do this. And that particular chemical, if I expand it, would be a carbon here, a carbon here, and a carbon here. This goes to an oxygen and a hydrogen. So I'm not going to put a carbon at that end. This carbon has 1 bond already, so it's going to have 3 hydrogens. This carbon has 2 bonds already, so it's going to have 2 hydrogens. And this carbon has 2 bonds already, so it's going to have 2 hydrogens. So this chemical that I just drew to you that looked like this is actually this chemical, and this is nothing more than propanol. Okay, probably the most famous chemical that's drawn through this type of notation. This, by the way, is called the stick notation. And if you go on to take organic chemistry, then this is how we do it. The most infamous chemical that has the stick notation is this chemical right here. This is what we call benzene. Okay, and you can see it's a hexagon, but what I can do is I can expand it. There's a carbon here. There's a carbon here. Let me change my pen so you guys can see this. There's a carbon here. There's a carbon here. There's a carbon here. So wherever the line bends or stops, I have a carbon. And then carbon always has 4 bonds. And so the hydrogens are implied. So this carbon has 1, 2, 3 bonds. That means it needs a 4th one. That's hydrogen. This carbon has 1, 2, 3 bonds. So that 4th one is a hydrogen. Likewise with this, that 4th one is a hydrogen. 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 So this chemical benzene is actually C6H6. Okay. So that's your stick notation. That's a crash course on the stick notation. And the reason why I'm showing you that stick notation, because now we go back to caffeine here. Now we can see that this is a carbon, this is a carbon, this is a carbon, and this is a carbon. Okay. Each of those carbons have 4 bonds. Count them. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. This carbon, it's condensed. This is actually a carbon that's attached to a nitrogen, and then the 3 hydrogens are like that. That's why we write it as CH3. Okay, that carbon also has 4 bonds. Now, the question here might be, complete the Lewis structure. If I want to complete the Lewis structure, let me clear out my picture here. Then you see how this oxygen only has 4 valence electrons so far, 2 from here and 2 from here? Well, that needs to be completed. You see how this nitrogen has only 6 valence electrons around it? 2, 4, 6. Well, that needs to be completed. Hydrogens are certainly satisfied with duet, 2 electrons. So to complete this Lewis structure, I need to do this. 2, 4. Now that oxygen has an octet. That oxygen also needs to have a complete octet. That nitrogen needs an octet. Now it has 8. That nitrogen needs an octet. Now it has 8. That nitrogen needs an octet. Now it has 8. And the way you put 8 around it is you put these lone pairs. Now the question is, what are the geometries around each of these central atoms? So let me go ahead and label these so that you can see what I'm doing. I'm going to say that this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, this is 9, and this is 10. This is 11 up here, okay? The reason why I don't put a number on that, that's not a central atom. That's a terminal atom. Likewise here, that's a terminal atom. Likewise here, that's terminal atom. So there are no geometries around that. Oh, the last one I forgot is this, 12. So around this carbon, remember there are 4 electron domains. It looks like this. And then that other bond is to the nitrogen, which is that right there. That's tetrahedral. And how do I know that? Because I have 4 regions of electron density, and all 4 regions have bonded atom at the end. And so that's automatically tetrahedral. Likewise, this is tetrahedral. This is tetrahedral. It's that easy. Once you figure it out, you can see which of the atoms, central atoms, are what the geometries are. Okay? Yeah, the hydrogens don't have to be written in the stick notation because they are implied. There's a question from Barry in the discussion board. Okay? Yeah, if you don't write the hydrogens unless you're certain parts. To make it clear, you do write the hydrogens, like in this particular example, but for the most part in organic chemistry, if I don't have this here and I only see that this carbon has 1, 2, 3 bonds, then I know that there's a hydrogen that's attached to that carbon. I just know it because that's what is implied in this stick notation. If carbon has less than 3, 4 bonds, then you have to put in that information that in order to give it 4, it's connected to hydrogen. Okay, so we've taken care of these atoms right here in terms of the molecular geometry. Let me clear the slate again. So how about this carbon right here? Well, look at it, has 8, but it's got 3 regions of electron density. That's a trigonal geometry. That's a trigonal geometry. It's AE3, but each of those regions of electron density are bonded atoms, so it's AB3, that's trigonal planar. Likewise, this carbon is trigonal planar. Likewise, this carbon's trigonal planar. Likewise, this carbon's trigonal planar. Likewise, this carbon's trigonal planar. All those carbons right there are trigonal planar because they all have 3 regions of electron density. And at the end of those 3 regions, there are bonded atoms. So it's trigonal planar. See this atom, this central atom right here? That's 1, 2, 3 right here. Even though that's a double bond, it's counted as one region because it's pointing in one direction. That's why it's an AE3. And at the end of each of those are bonded atoms, AB3. Okay? So again, we're taking what we learn in terms of the VSEPR and then extending it to more complicated chemical. Our last analysis are these nitrogens right here. You can see it's got 1, 2, 3 regions of electron density. This has 1, 2, 3, 4 regions of electron density. So this nitrogen and this nitrogen are different. This has 3, so we say it's AE3, and 2 are bonded atoms, so it's AB2E. So this is actually a bent tetragonal because the trigonal comes from the fact that its skeleton framework is AE3. Okay, so it's bent trigonal. This right here, however, it's got 4 regions of electron density. Let me change my pen. 1, 2, 3, 4. So it's AE4. But 3 of these are bonded atoms, AB3E. So this particular geometry, if you go back to that table, is pyramidal. It's a pyramidal geometry. It's a pyramidal geometry. Likewise here, okay, that's a pyramid geometry. So what you will see in some of my exam questions is I will give you a chemical. I would number these central atoms and I will ask you what is the geometry around each central atom. And it's not difficult to do. All you've got to do is look at each central atom, count the number of electron domains that is shooting out, come up with the electronic geometry designation, figure out how many of those electron regions have bonded atom at the end, how many lone pairs remain, and from using that chart, you now know what the geometry is. So hopefully this makes sense, because it's really not that difficult once you have a systematic way of seeing how things are connected. And things are connected because you can't come up with the molecular geometry if you don't know the Lewis structure. And then in the next topic that we're covering, which is polarity, you can't determine if the chemical is polar or non-polar if you don't know the molecular geometry. So one concept is always dependent on the other. That's why it's so critical to be on task of staying with me on these concepts, because if you learn VSEPR without doing Lewis structure, you're going to get lost in terms of how do I know that there are lone pairs on that nitrogen? How do I know that it has that many bonds? Well, it comes from the Lewis structure. You got to know your Lewis structure. Here's the example that we just did, okay? Caffeine, like I said, where the red tells you that it's going to be trigonal, okay? That is the electronic geometry is trigonal. The blue tells you it's tetrahedral, as well as the green. So that just, here's AZT. Remember, this particular drug was instrumental in helping combat AIDS. So you can see that I developed this lesson plan way back in the early 90s. You guys can practice on that. There's many central atoms on carbon on this particular chemical. You see how I drew the hydrogen here? I didn't have to do that, but I did that. If I didn't draw the hydrogen there, if I just drew this, if I just drew this for this carbon, then or even if I didn't draw the carbon, if I just did this, okay, then you would say that, oh yeah, there's a band there, that's a carbon. That carbon has 3 bonds already, the 4th one must be a hydrogen. You have to know that, especially if you're going to take organic chemistry. Those are just things that are assumed that you know. What we do is we sacrifice being detailed in terms of how we draw the structure so that we can draw it fast, but it requires the reader, the person who's looking at that chemical, to know that information, okay? So for simplicity's sake, the reader has to be able to make the adjustment and know what's being implied. Okay, so let's take a look at this right here, okay? The key to doing this problem is to make sure you understand how many regions of electron density you have. So I'm gonna find a pen real quick. Oxygen 1, that's this right here. That's this. Look at the region of electron density around that oxygen. There's 1 region, there's 2 regions, there's 3 regions, there's 4 regions. We did this in lab. That's an AE4. There's 4 regions of electron density. Look at the VSEPR rules. Of these 4 regions of electron density, there's 2 bonded atoms at the end. So that's an AB2, E2. If you look up that in the Lewis VSEPR table, that's a bent geometry. So oxygen 1 would be bent. Let me clear this slate. Okay. And you can easily do this. This carbon right here has 4 regions of electron density. That's tetrahedral. This carbon right here has 4 regions of electron density. That's tetrahedral. This oxygen right here, 4 regions, but 2 of them are electrons. That's a bent tetrahedral. This carbon right here has 3 regions of electron density. That's a tetrahedral geometry. So you just go through each, you just have to go through each atom. I'm sorry that so there's a delay there, and look at that central atom and count the spokes coming out of each central atom, and each central atom has a geometry around it. Each central atom has a geometry around it, and so you're going to be citing different geometries. Okay, so it's like I said, you made it. You may have made it more difficult than it is. You're not looking at just one molecule anymore. What you're doing is, yes, you could have used the table. It's an online. It's not required that you get. In fact, you know, the things that you got to remember is that we've changed the game for you. You guys are using don't use other folks to do your exam, but use the resources available. You guys could use the table in order to figure this out. And the table, I remind you, looks like this. Let me just pull it out real quick so that you guys can see. That's a table that you guys will use in order to look at each central atom and figure out what the geometry is, because there are multiple geometries. So for this particular example, yeah, that's a trigonoplanar. There's 3 regions of electron density, 1, 2, 3. 3 regions of electron density is a trigonal electronic geometry. There's bonded atoms in all 3 sites. All 3 sites, that's 1 region, that's the 2nd region, that's the 3rd region. That's a trigonoplanar. That's trigonoplanar right there. Okay, right? You can see that like N8 has 1 region, 2 region, 3 region, 4 region. 4 regions and 3 bonded atoms. 4 regions, 3 bonded atoms, 1 lone pair. That's a pyramid. That's the geometry around that. And that's what you would have selected over here. You would have said that it's a pyramidal. Okay, pyramidal. Oxygen here, that's not a central atom. It only has 1 bond. Anything that only has 1 bond or 1 other attachment are not central atoms. Central atoms need to be attached to 2 different atoms. So here are other chemicals. What I'm going to do now, so we're pretty much done with this particular section, is I want to go and I'm going to show you a site where you can figure out molecular geometry. I'm doing sort of the molecular geometry lab for next week, and I always have ideas on getting you guys exposed to the latest technology out there. So what I'm going to do is I'm going to show you this right here. So this site is called Molecular View. I'm going to close this. This right here is just that chemical that we did, caffeine, and you can build this chemical and then you can see the 3D structure of it. So you can see the geometry. You can see that this CH3 group here, and you notice there's no carbon there. That's because it's implied that that's a carbon, and because there's only 1 bond on that carbon, the hydrogens are going to be there. And so let me try and get you the proper perspective here. It's basically, what I have is basically, I think that, okay? See this carbon? That carbon right there, it has 3 hydrogens. That's a nitrogen. Look at the geometry around that nitrogen. It's trigonoplanar. Look at the geometry around this carbon. It's also trigonoplanar. Look at the geometry around this carbon. It's trigonoplanar as well. Look at the geometry around this carbon. It's tetrahedral. Look at the geometry around this nitrogen. It's trigonoplanar. And so the geometry comes from the fact that when you put it together based on the electronic geometry. So let me go ahead and make urea for you. Okay, I'm going to clear this. Urea has a structure of carbon in the center. So I'm going to put carbon in the center. And there's a double bond. And that double bond is to the oxygen. And then there are single bonds. And that single bond goes to nitrogen. And there's another single bond. And that single bond goes to nitrogen. I'm not putting any hydrogens, although I can. I can do this. I can do 1, 2, and then put hydrogens at the end. And then another 1, 2, and put hydrogens at the end. Notice I didn't put a carbon there because that carbon's implied. I'm going to clean this up. So I'm going to take my broom and clean it up. It's going to minimize the energy. And that's the structure. Then I'm going to render it to a 3D structure. That's urea right there. Okay. It's got, see how this nitrogen has 3 electron domains, but if you did the Lewis structure, you will see that there's a lone pair on that nitrogen. You can't do it here on this molecular geometry, but if you did it on paper and you did the Lewis structure, you will see that this nitrogen only has 6 bonds, 6 valence electrons. That means that the 8th, the 7th and 8th has to be lone pair. This nitrogen likewise has only 3 bonds, 6 valence electrons. The 7th and 8th electrons are lone pair. This oxygen only has 4 valence electrons. There are 2 lone pairs on that. But that's the geometry right there. Okay, we can make this smaller. Okay, by doing the pinch thing. Let me just clear this out. Let me do this guy right here. Okay, and taking that shape. And then I'm going to make benzoic acid. Benzoic acid is a benzene ring. This is just a hexagon. In order for it to be a benzene ring, I need to put a double bond here, a double bond here, and a double bond here. So I'm just clicking there with that single bond, meaning I'm adding a double bond. Then I'm going to put a single bond here, and then I'm going to put a double bond of that carbon, a single bond of that carbon. I'm going to put an oxygen at the end of this. I'm going to put an oxygen at the end of that. And then I'm going to put one more bond here, make that hydrogen. That right there is benzoic acid. I'm going to clean it up. Okay. Again, the cleaning up minimizes the energy and makes my geometry optimum. And then I'm going to render it to a 3D structure. Here's benzoic acid. Okay, now let's say I want to take this benzoic acid and I want to know whether this chemical is polar or non-polar. So I'm going to another program here called ChemDL. And then I'm just going to put here in this finer benzoic acid. Here it is right here. It's going to find that structure in the library. Here it is right here. Okay, that's so let me go ahead and do a pop window so that you guys can see this better. And I see it's not showing up on screen. Let me make sure that you guys can see that in terms of the window. Let me share that screen. Okay, so here it is right here. It's a pop-up screen. But the more important thing about this particular diagram is that over here under properties, I don't know if you can see that, but if you look here on this properties, I can cause this chemical to spin. Okay. I can change this so I can see the atomic radius. So this would be a space filling model. I can even see the bond length. It'll tell me how long these bonds are. I can look at the bond angle. It'll give me an idea of what the bond angles are. See if I can blow this up. So here you can see the bond angle, hopefully. It's kind of crowded. I can label the atoms so I know what atoms I'm talking about here, okay? I can see where the partial charge are. I can remove the labels, but more importantly, I can look at the molecular dipoles. And the molecular dipole tells me where the concentration of the electron density is found. Okay, that's the molecular dipole. So let me go ahead and change that. Molecular dipoles right here. That chemical has most of its electron density pointing in that direction. And then I can look at the bond dipole. I can see where that bond dipole lies. Within each bond, which one has a greater attraction for electrons. So this is ChemDL. Reason why I know about this side is I was actually an author in one of these snippets in this back in 2012, where I went to Washington, D.C. to work on some of the modules here. But this is a pretty cool site in terms of giving you information about the chemical. Okay, so again, you can use this site right here. It's called MoView. It's going to be in your next week's active experiment where you can create molecules and then render it into a 3D geometry. And then if you want to see properties of that chemical, then you can go to a site called ChemEdDL, or just ChemDL for short. You got to know the name or the formula. And then if it's in the library, it'll look it up for you. Okay. Yeah, it's a really cool site in terms of that. So if when we do molecular geometry, you guys will have a chance to play around with it. Yeah, there's a lot of pretty. You guys are pretty smart in terms of your generation. You do a lot of coding, and so the people who know coding actually figured out this program. So what I'm going to do is in the next few minutes, I'm going to introduce to you how we can determine molecular polarity of chemicals, okay? And it'll be pretty quick because it's just a buildup of what you guys already know. So